Hi, so now I'm going to put the data into my spreadsheet to analyse the results from my current balance experiment to determine the flux density of that major magnet. As you can see over here, this is where I'll be inputting the data for the current balance. This space here is for my results for a search coil with the same magnet. Those data are already inputted and I got 250 millitesla for the flux density for the magnet. So I'll be comparing that with what I get for the current balance. That's where I'm inputting the data, and then just down here is where I'll get a graph. I'm going to look at the graph, and the gradient will be equal. The gradient will be equal to B times L, the flux density times the length of the wire in the magnet. And so if I rearrange that, once I've got my gradient value, I can determine the flux density with gradient and the length of the wire. So what we're going to do is put the mass data in first. So I'll be getting the two mass readings I was getting from the balance, get an average, calculate the force from that, and then I'll plot down here force versus the current. I've already input the current values in there. So let's put these results in and see what we get. So 0.53, 0.52. Okay, so those are the results inputted. The average mass is here. This is in grams, so I need to divide that by 1,000 in order to convert it to kilograms. And then I'm using the weight equation, W equals mg, to work out the corresponding force from that. So that's what goes into this cell here, including the mass conversion divided by 1,000. Okay, so we've got all the force and current data. So now we plot the graph of that, current along the x-axis, force on the y-axis. We're getting a reasonable straight line there. It's got quite a small y-intercept, so it is roughly going through the origin. That's pretty reasonable. So what I need to do now is take this value here. This is the gradient value. If I zoom in on that so you can see that more clearly, this is our equation, y equals mx plus c. This value here is the gradient, 0.0103. So if I scroll up here, I've got a space to write that in. So 0.0103. And we're calculating the flux density there. So it's coming out as 206 millitesla. I've divided that by the length of the wire that was in the magnet. I just measured the length of the magnet and assumed that that would correspond. So that was 5 centimetres, so that's 0.05 metres. If I open that up, see I've got the value, the gradient value divided by 0.05. The reason for that is the equation that corresponds to this line is F equals BIL, and F is my Y variable, I is my X variable, so the two terms multiplied by I, which are B and L, are equal to the gradient. So that's where this comes from. BL equals gradient. I've rearranged that. As you can see, that is right order of magnitude to compare with my search coil data, but the search coil is about 20% bigger. So there is quite a big discrepancy there. I'm going to get some new data for the search coil and see how that compares. So I'll do that in the video about the search coil as an alternative way of measuring flux density.